Hello, and welcome to Aggressive Physics. Today is day 71, and what we're going to talk about today is Hooke's Law. Now, if we're going to discuss the second type of potential energy, which is elastic potential energy, we need to talk about how things work that stretch. And one of the things that stretches in a consistent manner is a spring. Now, a spring is something that will stretch when a force is applied to it, but then try to pull back on that force as you try to pull even farther. So you have resistance when you apply a force to a spring. So what happens is, in order to stretch a spring farther, you're going to have to apply even more force. So what's odd about a spring is that the force is not going to be constant depending upon how far you stretch it. In fact, it was Robert Hooke who studied this. And Robert Hooke determined that the force of the spring and the elongation was related to a certain variable called the spring constant for each specific spring. Now, not all springs experience this nice linear relationship. In fact, if you stretch a slinky out too far, you're going to exceed its elastic limit and you're going to break it. It's never going to restore back to its original position. What we're going to deal with, though, is with springs that restore back to their original position. Now, like I said, what's odd about a spring is it fights back. And Robert Hooke, when he came up with this, came up with what we now call Hooke's Law, and it's F equals Kx. Now, F is the force that you apply to the spring, K is the spring constant, and X is the elongation of the spring. Now, elongation is measured from the bottom of the spring to the bottom of the spring when the spring is stretched. It does not include the entire length of the spring. So it's how much it stretches from its rest position, not the total length of the spring. Basically, the force is going to be measured in newtons, the elongation is going to be measured in meters, and therefore the spring constant is going to be measured in newtons per meter. Every spring has a certain value that is known as its spring constant, as long as you don't exceed the limit of the spring, and that value will give a measure of the stretchiness of the spring. The bigger value for K, the stiffer the spring and more difficult it will be to stretch. So a small spring constant will be easier to stretch, and a large spring constant will be very difficult to stretch. That being said, as long as we're within the elastic limit of the spring, you'll get a nice linear relationship that you can actually graph. In fact, if you were to graph the force versus the elongation, you'll be able to find the spring's constant. And that's typically something that we cover in the laboratory setting. In fact, we try to determine the spring constant of different springs based on how much force we're applying. Now, a great, efficient, and consistent force is the force due to gravity. So we'll often hold the springs vertically and allow them to stretch. And when they stretch, we can measure how much it has moved, the elongation, and then calculate the spring constant from that. But graphically, it will show a nice linear relationship that starts at the origin. As long as you're within the elastic limit, then you can find the slope of the graph, and that will find you K. If you exceed the elastic limit, well, then you're going to get a curved graph, and then K will change. So what we're going to deal with in this course is springs that are within the limit of its elasticity. We're not going to go too far with the spring and then effectively ruin the spring. So the spring constant can be found by doing F equals Kx. K is the spring constant. Or we can find the spring constant by graphing the F on the y-axis and the X on the x-axis. Fortunately, X is on the X. And we can find the slope, which will yield the spring constant directly. So there's different ways mathematically and graphically that we can find the spring constant for a spring. Now, of course, this doesn't get us to our potential energy in the spring, and that's our discussion for another day. For now, though, let's look at a couple of practice problems with the whiteboard, and we'll solve for maybe the F or the X dealing with different types of springs. Thank you. All right. Now, springs are governed by Hooke's law. So Hooke's law states F equals Kx. F is the force applied. K is the spring constant. and x is elongation. What that means is that the force we're going to have in newtons, spring constant is newtons per meter, and elongation is in meters. As I pull on a spring, it will stretch farther. So one way to look at this is to take a spring, and this is usually a laboratory that we like to do. We would mark on a meter stick where the spring is before we add mass to it. And then once we add a mass, it's going to stretch out and possibly get to this point. So the elongation would be whatever this number is to this number. It's not the full length of the spring, it's only how much it's stretched from rest. So what I'll usually do is I'll look at the bottom coil and I'll compare it to the bottom coil with the extra mass on it. And the mass would hang down to here. I'll still measure the bottom coil. Now in the problem we're looking at here, this is where I put 150 grams on it, and this stretch is 12 centimeters. That being the case, the force is going to be due to the force of gravity, which is 0.15 kilograms times 9.8 meters per second squared. So you have 0.15 times 9.8, and you get 1.47 newtons. That becomes the force that you're applying. The elongation is 12. 1.47 newtons equals K. Now the 12 we have to convert, 0.12 meters. And when we divide 1.47 divided by 0.12, we get the K to be 12.25 newtons per meter. Now that is a good way to compare springs. A large K means it's very stiff and difficult to stretch because it takes a lot of force to stretch it a little bit. A small K would be looser in terms of the spring. It would be much stretchier, much springier, if you will, and it would be much easier to pull. Now, of course, you can't compare a single number here to itself. You would need other springs, and then you can compare how stiff or springy they happen to be. But that's how we find K using Hooke's law. And this is some sample data that could have been collected in the laboratory setting. So where does the equation for potential energy of a spring come from? Well, if you look at the graph, this is a standard graph of force versus elongation for a spring. And as you'll see, as you stretch it farther, it takes more force. And that's because the spring is going to supply a restoring force so that as you stretch it, it's going to try to fight you back. So you have to pull even harder to get it to stretch farther. Now, the slope is change in y over change in x, which is f over x, which is equal to k. So the slope gets us the spring constant. Now, with that said, we have two pieces of information that we can get from a graph. And the second piece of information is the area. So, area of a triangle is 1/2 base times height. 1/2 because it's a triangle. It's 1/2 x times f. And since we already said that f equals kx, we can replace that with f equals 1/2 x kx. So the area becomes 1/2 kx squared. And if you remember from before, this is no different than a force times distance graph. So this is really the work done, and the work done is the potential energy that we gain. So 1/2 kx squared comes from this graph. There's a potential energy of a spring, and the equation is 1/2 kx squared.